In this lecture, we're going to examine the 4 different types of conformations that cyclohexane can take. Now, cyclohexane is one of the most stable, lowest in energy cycloalkane in organic chemistry, and that's exactly why it predominates as a ring structure. So, let's begin by examining the following diagram. So the y-axis is the energy axis. In other words, the higher we go, the more energy we have, the lower we go, the less energy we have. Now letters A through G represent our various types of conformations that cyclohexane can take. Now, the higher on the y-axis we go, the more energy our conformation has, the less stable it is. Likewise, the lower we go, the less energy it has, and the more stable our conformation is. Now, let's begin by examining conformation A and conformation G. These two conformations have the same exact energy, and they represent the lowest possible energy conformation. And A is given by the following structure, and G is given by this structure here. Now, these structures, A and G, are known as chair conformations. These conformations are the most stable. They're lowest in energy, and they're known as energy minima. Energy minima simply means these compounds, these conformations, can be isolated. They're lower in energy than most other, in fact, than all other conformations. Now, let's look at B and F. B and F, unlike A and G, are the highest possible energy conformations, and they're given by structure B and structure F. Now, B and F represent transition states. What that means is their energy maxima. They cannot be isolated. That's because they're so high up in energy, they're so unstable, that they will only exist for a very, very short period of time. In other words, when A becomes C, it has to go through D. But because B is a transition state, B cannot be isolated. We can isolate A, C, and E, and G because all of these are energy minima, but we cannot isolate B, D, F because they're transition states, they're energy maxima. So, B and F are known as half-chair conformations, and these have planar structure and lots of angle and torsional strain, and this represents energy maxima, and that means they cannot be isolated. So now let's look at C and E. So C and E are energy minima. They're higher in energy than A or G, but they're still energy minima. And that means they can be isolated like A and G can. Now C and E are given by the following 2 structures, which look like bow ties. And these are known as twist conformations. Once again, they represent energy minima, and they can be isolated. Now let's look at the final type of structure, conformation D. Conformation D is a transition state like B and F, but it's lower in energy than either B or F. So, this is known as the full boat conformation, and it's given by the following structure. This has torsional strain as well as van der Waals strain. And this represents our energy maxima. It's a transition state. It cannot be isolated. So, let's examine why is it that our chair conformations are the most stable while our number 2 half-chair conformations and full boat conformations least stable. Why are they transition states? So let's begin with our chair conformation. So chair conformation looks like this. This is conformation A. Here we have our H atoms. We have 6 axial and 6 equatorial H atoms. Now, all the H groups are as far away from one another as possible. And this means the angle between our 2 bonds will be an ideal angle, or very close to ideal. And so our electrostatic repulsion between the electrons in the different bonds is minimized, and that means we have very little or even no angle strain. So we have very little angle strain and very little torsional strain. So our molecules, our atoms, H atoms, will be staggered in the staggered conformation. Now, let's examine our half-chair conformations B and F, given by these two structures here. So here we have B. So why is it that this conformation is the highest in energy? Well, that's because it contains eclipsed H atoms, and this eclipsed conformation leads to torsional strain between our H atoms. So that's exactly why these two structures, B and F, will be our transition states. They'll be high in energy. Now let's examine the full boat conformation given by D, which is here. So it's a transition state, another transition state. So earlier we mentioned van der Waals strain forces. What is that and what causes it? So notice that in this conformation we have two H atoms that in a way interact. They bump one another, they interact. And this is known as electrostatic repulsion. The electrons within these two atoms will repel one another. This will create destabilizing effect. And this is known as van der Waals strain. So this will cause this boat conformation, full boat conformation, to exist as a transition state. So once again, the most stable conformations of cyclohexane are A and G and are known as chair conformations. When we have a very low temperature, when we have no energy available, our two conformations will only be A and G. But if we have a lot of energy available, for example, if we're at room temperature, that will give us enough energy to overcome these two humps. And A and G will also exist as C and E. So if we have enough energy, our cyclohexane will exist as A, G, C, and E, but no matter how much energy we have, it will never exist as B, D, and F, because these represent transition states. But if we have no or very little energy, our cyclohexane will exist strictly as A and G, as the chair conformations.